Hello, students. So, today we will continue our discussion on thermodynamics that we started in the last class. Like in the last 8 lectures, we have understood how we can define specific parameters of thermodynamics. And in the last class, we learned about the techniques. The techniques are shown over here. That are the standard enthalpy change of fusion and vaporization. Now, in today's class of thermodynamics, we will learn about something new. Now, in this case, also, we will talk about the enthalpy change, that are the standard molar enthalpies of formation, that is delta FH minus at 25 degrees Celsius, that is 298 Kelvin. So we will continue our discussion, and first of all, I will show you a table. So this table here is consisting of some standard molar enthalpies of formation at 298 Kelvin of few selected molecules. So we have some substances, and we have the delta FH minus, that is the standard enthalpy of formation of these compounds. This F suffix that you are seeing over here, let me just take up the marker here. Yes, this F suffix. This F is actually standing for formation. So that's why it is termed as delta FH minus at 298 Kelvin. These are the substances: aluminium oxide, delta FH minus in kilojoule per mole. We have different kinds of compounds over here. We have Al2O3, we have barium carbonate, we have bromine liquid, bromine gas, and whatnot. So in this table, we have a number of substances whose delta FH minus is given. Now, a question may arise in your mind that what is meant by delta FH minus. Now, this minus sign stands for the standard state. So, the standard enthalpy change for the formation of 1 mole of a compound from its elements in their most stable states of aggregation, also known as the reference states, is called standard molar enthalpy of formation. Its symbol is delta FH minus, but the subscript, that is F, stands for the 1 mole of the compound that has been formed in its standard state. Now, in this case, the standard state formation will be composing of the all the elements in their most stable states of aggregation. The reference state of an element is its most stable state of aggregation at 25 degrees Celsius and 1 bar of pressure. For example, the reference state of dihydrogen is hydrogen gas. Also, those of dioxygen, carbon, and sulfur will be O2 gas, carbon graphite, and S rhombic, respectively. So we have several reference states for each of the element. So it will be first characterized at 25 degrees Celsius and 1 bar of pressure. So we have F for formation, and we have the standard enthalpy change, that is the delta FH minus. So it will be the formation of 1 mole of a compound from its element in their most stable states of aggregation. So I guess you have understood the fact that delta FH minus, whenever we will talk about delta FH minus, it will be at 298 Kelvin, that is 25 degrees Celsius temperature. So here we have several molecules we have ethanol, we have carbon diamond and carbon graphite. Among these things, you will see there will be several molecules or substances which have delta FH minus equal to 0. So here, what are those? First is this bromine liquid. It has the delta FH minus equal to 0. And if you look at the table, you will see there will be several other molecules which have H2 gas that it has a delta FH minus equal to 0 that you can see over here. We have another gas which has a delta FH minus equal to 0, that is Cl2. So here on the right hand side, you can see we have Fe2O3, we have chlorine monoatomic gas, H gas, carbon gas, SiCl4, and likewise we have many such substances. We have the delta FH minus value of these two. Now there will be some equations for you to understand what are these. So firstly, there will be many reference states. It can be for oxygen, it is oxygen gas. For carbon, it is carbon graphite. For sulfur, it is its rhombic state. Now I will put up some examples for you so that you can better understand how the standard molar enthalpy of formations are given below. We have the H2 gas. We have the O2 gas. So if H2 plus half O2 gets combined, it will be H2O. And it will be formed in the liquid state. So H2O gas plus half O2 gas will form H2O liquid. So delta FH minus will be minus 285.8 kilojoule per mole. So it is the standard molar enthalpy of formation for H2O liquid. So here H2 gas 1 mole and half mole of O2 gas will form H2O liquid. Delta FH minus is equal to minus 285.8 kilojoule per mole. Now carbon graphite, that is solid. And it will be equal, and here we will have with carbon graphite, that is solid, and here we have 2 moles of hydrogen on the reactant side. So it will be 2H2 gas, and we will form CH4 gas. So we have carbon graphite solid on the left hand side. We have 2 moles of hydrogen on the left hand side. If both of them combine, we form the methane gas. So if you are asked that what is the equation for standard molar enthalpy of formation for methane gas, we will need to write this equation. When you are given this equation, that is carbon graphite that is in solid state and 2 moles of hydrogen is formed, we are having this methane. So one note you will be having here, whenever you are asked, like tell me what is the standard enthalpy of formation of H2O. What is the equation? You will see what are the components here. One is hydrogen, one is oxygen. So you have to know what is the standard state of hydrogen here, which is H2 gas, and what is the standard state of oxygen here, which is O2 gas. So you have to then write H2 plus O2 to H2O liquid, and then you have to balance the equation to get the actual chemically balanced equation. Similarly, if you are asked what is the standard enthalpy of formation of methane, you will see you have the carbon element and the hydrogen element. For hydrogen, the gas element is H2, and for carbon, it is graphite, that is solid. And now we have carbon plus H2 to CH4. And then we will try to balance this equation to get the actually chemically balanced equation. So for this reaction, the delta FH minus will be minus 74.81 kilojoule per mole. So for the first equation, we have H2 plus half O2 to H2O liquid. For the second equation, we have carbon graphite solid plus 2H2 gas to CH4, which has a delta FH minus value of minus 74. So now we have the standard enthalpy of formation of C2H5OH, that is ethanol. So if you were asked like what is the standard enthalpy of formation of ethanol, what will it be? So we have ethanol over here. So if you know the ethanol is written as this, that is CH3. In the organic chemistry class, you might have known about the molecule that is ethanol, which is CH3 CH2OH. Or if you club all the atoms over here, it will be C2H5OH. So this is the molecule we have. So we have what are the elements over here? We have carbon, we have hydrogen, and we have oxygen. So we have carbon, we have hydrogen, and we have oxygen. So these are the elements by which we can form ethanol. So now we have to write this in their standard state. So for carbon, the standard state is, as you can see over here, it is carbon graphite in its solid state. So carbon graphite in its solid state is carbon solid. Next, we have hydrogen gas. Hydrogen gas's standard state is H2 gas. And we have oxygen gas. So we will write O2 gas. So carbon is solid, hydrogen is solid, and oxygen is carbon is solid, hydrogen is gaseous, and oxygen is gaseous. Now we will form the compound that is C2H5OH. Which is liquid. Now for this reaction, the delta FH value is minus 277 kilojoule per mole. But we have to first balance this equation to get it. Because whenever we will talk about any chemical equation, we have to make sure that we are balancing the same. So here if we try to balance, On the right hand side, we have 2 carbon atoms. So we'll write 2 over here to make the carbon atoms same. So we have 2 carbon atoms. We have 6 hydrogens over here, one H5 and one is the OH. So we have 6 hydrogen atoms. So we have 3. So we'll put 3 over here because 3 into 2, it will be 6. And we have 1 oxygen atom over here, but we have 2 oxygen atoms over here. So we will multiply this by half. So it will be 2C plus 3H2 plus half O2 will generate C2H5OH, which is the standard enthalpy of formation of ethanol, that is minus of 277 kilojoule per mole. Now we'll come up to the next section, that it is very important to understand that a standard molar enthalpy of formation, that is delta FH minus, which is discussed over here, is just the special case of delta RH minus. That is the reaction when 1 mole of compound is formed from its constituent elements, as in the above 3 equation, where 1 mole of each water and methane and ethanol is formed. In contrast, the enthalpy change for an exothermic reaction, that is calcium oxide and carbon dioxide, if these two react, we form calcium carbonate. It is not an enthalpy of formation of calcium carbonate, because let us take a reaction which is as calcium oxide in solid state. We have CO2 in gaseous state. We have CaCO3, which is also in its solid state. So this is a reaction where it will be del RH minus, because it is a reaction enthalpy. So del RH minus of this reaction is minus 178 kilojoule per mole. But you have to understand that it is not a delta FH minus. This is not a standard enthalpy of formation. No, it is not. It is not. But this is right for the reaction, that is delta RH minus, standard enthalpy of reaction. Why? Because you see, this is the product which is calcium carbonate. But to form calcium carbonate and to have the delta FH minus, we have to have the reaction from calcium, that is solid in its elemental state, carbon in graphite state, and oxygen in its gaseous state. So these 3 components should be present for the standard enthalpy of formation, that is calcium carbonate. We have calcium oxide on the left hand side and CO2 on the left hand side. So none of the calcium oxide and CO2 is the constituent element of calcium carbonate. This is simply a reaction between 2 different compounds, that is calcium oxide, that is soda lime, and CO2, that is carbon dioxide, to form calcium carbonate. So this is specifically a reaction. That's why it is termed as the del RH minus. So it is not the delta FH minus. It is not the standard enthalpy of formation of calcium carbonate. So we have calcium. If we had carbon and if we had oxygen, then we would have formed calcium carbonate to make the delta FH minus, which is not shown here. So it is not the enthalpy formation, because calcium carbonate has been formed from other compounds, that is calcium oxide and CO2. Also, for the reaction given below, the enthalpy change is not standard enthalpy of formation, because if we also carry out the reaction H2 gas plus Br2 gas, or Br2 actually it's liquid at a normal temperature, so it will be Br2 liquid. it will form 2 moles of HBr gas. So if from H2 gas and bromine liquid we are forming 2 moles of HBr gas, the del RH minus is minus 72.8 kilojoule per mole. That is del RH minus. And because here 2 moles instead of 1 mole of the product is formed from the elements. Because here you can see 1 mole of HBr is not prepared. We have prepared 2 moles of HBr. Now let's see, let's say that we are dividing this equation by 2 on both sides. So we have now half H2 plus half Br2. I am not mentioning the states over here because it is as shown on the top equation. Now we will form HBr. Now here you can say like, yes sir, in this case 1 mole of HBr is formed, and that we may term as the delta FH minus. So one thing is very clear here, that del RH minus is just the double of the delta FH minus. So delta HF minus will be minus 36.4 gram per mole. So we have delta FH minus and we have delta RH minus. So delta FH minus and delta RH minus will be just the half of del RH minus. So this is the equation, because when we are dividing this by 2, we are getting the equation which forms the delta FH minus, because 1 mole of HBr is formed from half moles of H2 and half moles of Br2. And this is also the equation where 1 mole of H2 and 1 mole of bromine forms 2 moles of HBr. That is having the del RH minus. So here in this case, you see the standard enthalpy of formation of some common substances is this one, that is the delta FH minus. That's why in the last slide, I have taken up this example where there are various substances and you can see they have all their delta FH minus value. Al2O3 from aluminium and oxygen, barium carbonate from barium, carbon and oxygen, bromine liquid is from its elemental state, that is 0, and now bromine gas is from bromine liquid to bromine gas. Any diatomic, any atomic liquid or gas in its elemental state will have the delta FH minus 0. That's why bromine liquid, chlorine that is gas in room temperature, and hydrogen gas in room temperature, they have all their delta FH minus as equal to 0. So bromine is liquid at room temperature. H2 is gas at room temperature. Also chlorine is gas at room temperature. So we have these 3 elements which at their normal standard state, that is 298 Kelvin temperature and 1 bar of pressure, they are in their elemental state. That's why their standard molar enthalpy of formation is equal to 0. Now let's move to the next discussion of ours in this class, which is regarding delta FH minus or del RH minus, where we'll be performing the specific kinds of reaction and we will see how we can be able to calculate it. So now we have the we can make use of the standard enthalpy of formation and calculate the enthalpy change of the reaction. So let's suppose you are an engineer, chemical engineer, and you want to know that how much heat is required to decompose calcium carbonate to calcium oxide, that is lime and carbon dioxide. So we have the equation calcium carbonate to we have calcium oxide, that is termed as lime plus CO2, which is carbon dioxide. Now we have to calculate del RH minus here. That is how much heat is required to decompose calcium carbonate to calcium oxide and CO2. So we have to calculate the del RH minus here. So in this case, the equation is over here. Now we can make use of the standard enthalpy of formation and calculate the enthalpy change of the reaction. So how we can calculate the standard in reaction enthalpy from the standard formation enthalpy? Now there will be a general equation for the enthalpy change calculation. So del RH minus that we have to calculate here, all are in its minus state, that is standard state. So I write minus on the top of the equation. So del RH will be summation of AI. I have in the last class told you what is meant by the summation sign. Summation means addition of specific components. Summation of AI delta FH of the products minus summation of I BI delta FH of reactant. So that is the common equation to calculate delta RH of a reaction. Summation of AI into del FH of product minus summation of BI del FH of the reactant. And now this what does this A and B, what do this A and B stand for? This A and B represent the coefficients of the products and reactants in the balanced chemical equation. So firstly, we have to balance the equation. In the equation, you can see the equation is balanced. We have one calcium on both sides. We have three oxygens on both sides and one carbon on the both of the sides. So we will apply the above equation for the decomposition of calcium carbonate. Here A and B both are equal to 1. So AI equal to BI equal to 1. So if we put AI and BI in this equation, we will have the delta FH minus of calcium oxide plus delta HF F minus of CO2. And we will subtract delta FH minus of calcium carbonate, which is the reactant. So if we put the value from here, what is the delta FH minus of calcium oxide? What is the value of CO2? And what is the value of calcium carbonate delta FH minus? We will put the values over here, which is 635.1 minus 393.5. This value will be given to you in the examination, where you will be easily able to put this and solve the equation, and minus of minus 1206.9. So ultimately, if you calculate this, we will have 178.3 kilojoule per mole. So the decomposition of calcium carbonate is an endothermic process. The del RH is actually negative. If positive. So del RH is positive, that means it is an endothermic process. So you have to heat it for getting the desired product. So for this reaction, it is not generated or evolved from the reaction mixture. Rather, we have to put some heat externally to the reaction so that it happens, because del RH is greater than 0. So it is an endothermic reaction. It is an endothermic reaction. And for an endothermic reaction, it will be, we have to put some heat to initiate the reaction. Now we will move to our next slide, which is the thermochemical equation slide. So every change which accompany chemical reaction is almost always expressed by a thermochemical equation. So what do we mean by thermochemical equation? A thermochemical equation is as shown over here. You can see CH4 plus 2O2, that is methane in its gaseous form, reacts with oxygen in its gaseous form to generate CO2 and H2O. So it will be carbon dioxide and water at 25 degrees Celsius and 1 atmospheric pressure. Delta HM is minus 890 kilojoule. Now, if we demonstrate the reaction on atomic level, we get an idea what this reaction looks like on the macroscopic level. So we will check out the flame on the right hand side, which is this one. It is in the macroscopic level, and this one is in the microscopic level. So here CH4 is this molecule, one carbon attached and 4 hydrogen atoms attached to it. We have 2 moles of oxygen molecules, O2, OO atoms are there. And there is a this methane molecule, which is tetrahedral in nature. Four hydrogen atoms. And we have 2 oxygen molecules, O double bond O. 2 oxygen molecules, they will react with each other and we will form CO2. CO2 is a linear molecule, O double bond C double bond O. So it is a neutral molecule CO2 and linear molecule, and we have 2 moles of water. Water is a bent molecule. The geometry of water is this one, H O H. So look carefully, we are dealing with a reaction which consists of methane and oxygen. So if you look carefully, you will see that these are CH4 plus O2 will deal with CO2 and H2O. So we had a tetrahedral molecule which is methane CH4, and we have a linear molecule which is oxygen O double bond O. Now we are generating OC double bond O, which is CO2 and H2O, which is in the microscopic level. So if we burn methane in air, we will form CO2 and H2O. Now, what happens on the macroscopic level in our outer world is shown on the right hand side. On the right hand side, you can see a bulb is actually blinked over here, and the temperature is minus 890 kilojoule per heat of energy. So that means in this reaction, minus 890 kilojoule energy is actually expelled out. That means it is an exothermic reaction. That's why on the right hand side you can see it is burning of methane. That is, gas is actually getting burnt off. Now here the delta Hm, that is written over here, delta Hm, which is minus 890 kilojoule per mole, tells us whether heat energy is released or absorbed when the reaction occurs as written. And also it enables us to find the actual quantity of energy involved. So by the natural convention, as I have told you in the last class, if delta Hm is positive, it is absorbed by the reaction. It is endothermic. More commonly, delta Hm is negative as in equation, indicating the heat energy is released rather than absorbed by the reaction. So it will be then exothermic. If delta Hm is negative also in this case, that means it is an exothermic reaction. So I guess you have now got the clear idea about the convention of sign to mention which is an endothermic reaction, which is an exothermic reaction. Where delta Hm is positive or negative looks at the change in terms of matter actually involved in the reaction rather than the surroundings. It is important to note that delta Hm is the energy for the reaction as written in the equation CH4 plus 2O2 to CHCO2 plus 2H2O. Q amount of heat quantity is absorbed or released, and N is the amount of substance involved. It is delta Hm is equal to Q by N. So 890.4 kilojoule energy is released for every 2 moles of water produced. Seen in this way, delta Hm is a conversion factor that will enable us to calculate the heat absorbed or released when a given amount of substance will be consumed or produced. So this is the final equation for our convenience, which is delta Hm is equal to Q divided by N, where Q is the quantity of heat absorbed or released and N is the amount of substance involved. It can be mole, it can be gram. So this thermochemical equation, the coefficients in a balanced thermochemical equation refer to the number of moles or not molecules of reactants and products involved in the reaction. The numerical value of del H minus refers to the number of moles of substances specified by the equation. Standard enthalpy change, that is del H minus, will have the unit kilojoule per mole. We have an example here that if we burn ethanol in air, that is oxygen, we will produce CO2 and H2O. Now, the above equation describes that the combustion of liquid ethanol at a constant temperature and pressure, it is negative. The negative sign is indicating that it is an exothermic process. So here, before going to the equation, I'll write something here for you. If we take the equation C2H5OH, and if we burn it in oxygen, we will form CO2 and H2O as expected. For your convenience, I will tell you that whenever a hydrocarbon is burnt with oxygen, the product will be is H2O. Yes. So the product will be CO2 and water. So you have to balance the equation first. On both the sides, we have 6 moles of hydrogen over here and we have only 2. So we will put 3 over here. So it will have 3 oxygens also. So hydrogen is balanced. So we have 3 oxygen on the right hand side. We have 1 carbon and we have 2 carbons over here. So we'll put 2 over here. So we have now 2 carbons on both sides. We have 4 plus 3, that is 7 oxygen atoms. But on the left hand side, we have 3 oxygen atoms. So if we put 3 over here, it will be 3 into O2, that is 6 oxygen plus 1, that is 7. So oxygen is balanced, 7 oxygens on both sides. Hydrogen is balanced. On both sides, we have 6 hydrogens. H5 plus 1, so 6. Here also we have 6. And we have 2 carbon atoms on the both sides. So we have now been able to balance the equation. Now the del H of the reaction, that is the standard enthalpy of reaction, it is minus 1367 kilojoule per mole. So as I have told you, that if the del H, so we have the del H minus, which is minus 1367 kilojoule per mole. So that means since del H minus is negative, so this reaction is an endothermic, not an endothermic process. Rather, it is an exothermic process. Since it is an exothermic process, that's why the heat energy is actually negative. So in this case, we have an exothermic process. To illustrate this concept, we have taken the equation how much heat energy is obtained when 1 kg of ethane gas, that is C2H6, is burnt in oxygen according to the equation. The equation is given over here, C2H6 plus O2 producing CO2 and H2O, that is water. So if we have to balance the equation, you see we have able to balance the equation. We have 4 carbon atoms on both sides. We have 12 hydrogen atoms on both sides, and we have 14 oxygen atoms on both the sides. So we have got this chemical equation, and now we will be able to see like how we can solve the question. The delta HM value is given as minus 3120 kilojoule. Now, how much heat energy is required, that is asked over here. Now, the mass of C2H6 is easily converted to the amount of C2H6 from the heat energy Q is easily calculated. Now, delta HM value, which is given over here, it is, you can see it is for 2 moles of ethane. 2 moles of ethane, for which we have the delta HM value minus 3120 kilojoule. Now, we have the road map over here. The mass of C2H6, by which by the amount, that is capital M, we have N of C2H6. And from then, if we put the energy delta HM, we will ultimately get the value of Q. So finally, we have got it, like how we can be able to solve it. So now we will be able to calculate the Q value. Q value is 1 into 10 to the power 3 grams. So here you can see for 1 kg of ethane gas, we have to calculate. So 1 kg means 10 to the power 3 gram. 10 to the power 3 gram of C2H6. Now we have got 1 mole of C2H6 divided by the molecular weight of C2H6, which is 30.07 gram, that is C2H6. So we have to calculate what is the amount of moles of ethane gas in 1 gram of ethane. So finally, we will be able to calculate it. We will divide 10 to the power 3 gram, that is the weight of the gas, divided by its molecular weight. C2H6 molecular weight is 2 into 12. 12 for carbon. And we have 6 hydrogen atoms. So 6 into 1. Total we have 30. So 30 is the molecular weight. So we have to divide 10 to the power 3 divided by 30.07 gram, which is the number of moles over here. Now, since the delta HM value is given for Q by N, that is 2 moles of C2H6, we have to again divide it by 2. So it will be divided, Q will be divided by 2. So minus 3120 kilojoule divided by 2 mole into the amount, that is 10 to the power 3 gram, divided by the molecular weight, that is 30.07. So ultimately we are getting this amount, that is minus 51.88 kilojoule, which is minus 51.88 megajoule. So ultimately we have got the amount, that is the how much heat energy is obtained when 1 kg of ethane gas is burnt in the open air or oxygen. So with this, we will stop today's discussion. Now, if you guys have any question or any query regarding any of the slides, you can go ahead and ask.